My, my talk will be about analytics on the data who are streamed. So no airflow, just a huge amount of data, so much of them that we can't store them and do SQL on them. It will be about our search results data. When I came to Kivicom, we haven't been storing any search results data, not even the searches. And since the data is the new gold in this new information age, I pushed the management that we should store all our search and search results data, which was pretty expensive, but beneficial. Just to think about it more, I'll give you a question. It's my favorite question for interviews, and this is it. Let's say we want to store all our search results in Amazon S3, and we do like 1,000 searches per second. What would be the cost? And you don't need to solve it now, but just think about how would you solve it. This is how our search results look like. So to estimate the cost of storing the data to S3, you would need the volume. You would need to know the volume of the data. How to get the volume of the data? You would probably go to our web page and investigate the communication between front end and back end. And what would you find out? That there is the API. I've already showed API call. I've already shown to you. And this is how the search response looks like. And usually the average volume of the search response is like 100 kilobytes of data. So if we are doing 1,000 requests per second, and one search response is this huge, you can kind of estimate what's the hugeness of our data stream if you want to store or process somehow. Why would we store this data? Why would we even like considering to process them somehow? Because we don't need to do that. We can just send the data as a response to our customer or to our meta search, and that's all. But there are actually 4 reasons. We can sell the data to somebody. We have actually some business partners where to whom we are selling the data, like a streaming directly to their servers. And we are discussing to do it with more customers. We can do the ticket price prediction. For example, let's say there is a customer who buys a ticket from Minsk to Oslo, and we somehow, with magic and machine learning, we knew that the price would get lower in 2 days. We can do that thing that we will actually sell the ticket to the customer, but not buy it in the airline. And we'll buy it in like 2 days, when it gets cheaper. So it's some kind of speculation with buying and selling the tickets. That would be also possible if we can do the price prediction. But how to do the price prediction? We need to teach the machine learning system to actually do the job. Talking about machine learning, we are still search engines. So we need to somehow sort the search results in the right order to put the most compelling one, where there is the biggest probability of clicking and booking, we need to put it as the first. Usually it's the cheapest, but sometimes the cheapest one doesn't mean the best one, because if the flight takes like 3 days and you need to wait on the airport through the night, it doesn't look good. And this is what machine learning is trying to guess, like to find out the attributes where the people are just buying it or where not. And also, it could be like different tastes, like people from Minsk may have a different opinion about some kind of airlines, so our airports. So maybe they're trying to avoid some kind of airports, or maybe also timing. Time is also important in this machine learning case, because I've heard about Ryanair is setting different prices in weekends and afternoons and evening, and also in the mornings. Because usually in the mornings, there are business customers active, and they don't care much about the price, so they just buy. But on the evenings, they are just common people buying the flight tickets for themselves, and they are like more sensitive to price. So this is what the machine learning needs to somehow feel from the people or analyze. And the last one is more like the simplest case, is that we need to monitor the conversion. You can imagine that as a graph, how many searches we are processing, and also there is another graph, how many bookings are we processing, and the ratio is somehow showing how good we are. If, for example, we do some design changes on our booking page, and somehow the amount of searches stay the same, but amount of bookings gets higher, it means that was a good design because we have improved the conversion rate from the search to the booking. And also it works the other way. And also we should not monitor the conversion just for the amount of searches in general, but just differently for different markets. If typically there is some holidays in Japan, usually there is like search results or search searches going down, and we need to investigate why it's happening. But the ratio may stay the same. Also there can be like technical issues, so we need to monitor the number of cases where we have actually returned nothing. That could happen, and we should be alerted about that. This is also our team's responsibility, like BI in this case. Okay, this is the reason why should we somehow process the data, but how we are actually doing that? We start like when I came to the company 3 years ago, and this is like a comparison of 3 different solutions. I have already forgot about the yellow one, so I'll just be talking about the blue one and the purple one here at the bottom. What the graph actually shows, this is the number of seconds how it took to store one bulk of the search results data into the database. The blue line is Postgres database, which is already full of terabytes of search results data. And you can see it's pretty unstable, and it took like half a minute to store the bulk of the search results, to build the indexes especially. And the purple one here, under the 1 second, it's BigQuery, streaming insert. So it looks like BigQuery is right solution for us, and it actually was by the time. Because with BigQuery, it behaves like a typical database. You can do this SQL select on it, and it's somehow distributed and super fast. But you are also paying for the selects. If you do the select which some kind of touches the 1 terabyte of data, I mean, which touches the indexes of 1 terabyte of data, you will pay $5 per select. So it's kind of weird. But it was not much, and it kind of works, but there were some new coming data scientists into the company, and we had tried different solutions. But have you heard about, I'm sure you have, column-based databases? Can you just show me who know what column-based database is? Okay, that's a lot, like 20%. Just a brief explanation. Why I'm talking about that, one of the reasons BigQuery is so fast is that not only it's distributed, but also it's column-based. This shows the organization of data physically on the disk. If I want to find, for example, the row which has the sales for 1,000, in this case, in the normal organization of data, I would need to go through lots of records to reach it. In this case, I would just start here. and go through this. And what's actually the header on the disk? What it's doing? It can't just skip some of the records because it's rotating. So it's much faster to just go through this at once. So it's faster because it's reading less data from the disks. It's not only disk because the database distributed across many data centers. Well, this is just one of the reasons. Well, I talked about data scientists coming to our company, and this is the traditional way how to deal with big data. I would say traditional, it's like, I don't know, normal for the last 5 years. So we have the search engine generating the search results. We store it in the Amazon S3, like, for example, zip files, like JSONs, but packed in zip files. And then we have some Hadoop Spark solution which extracts the data, do some computation on it, and put out the result. It actually worked. The size of daily data was about 2 terabytes. But it was not as cheap as we expected. That's one thing, because it was running on 15x large instances on AWS. Another thing is that for each task we want to compute, we needed to write a Python code, which was pretty unusable for most of our analytics because they are really good at SQL, but they don't know Python much. So it was not handy. It was kind of awkward to do the analysis on this system. So we have decided to just use different storages for different kind of forms of the same data. Yeah. To explain that, I'll start with async.io. Okay, let's say you want to make a breakfast. And this is what you can do in order to make a breakfast for you. Maybe you will know how to optimize this sequence. I'm pretty sure that you don't follow this sequence. There is actually 2 waitings, 1 and 1. So you would start pouring the water into the kettle, start heating it, and then you will just skip to number 4, put eggs into water, and you will be waiting on, like, in parallel, right? It actually makes more sense to be able to wait 2 times. You're not doing actually 2 things. It's not parallelism. It's called concurrency. And that's what is async.io about. So to put it in the code, you can maybe guess which of these messages goes first on the screen. Well, the first method, or the method, say, will do that, it will sleep sometime and then say something. And since this should wait 2 seconds and say something, and this should say 1 second and wait and say something, the order gets switched because it's, in some point, it is waiting in parallel in the same time. Why I'm talking about that? Because it's handy for data pumps. If you have some software which works like a data pump, which means reading some data from something, doing some cheap transformation with the data, and then sending the data to somewhere else, most of the time, I mean the real time, is just waiting for the input device or just waiting for the output device. You need to do the concurrency in this thing. And async.io is a great way how to do the concurrency. You are waiting for the eggs, and also you are waiting for the tea kettle in the same time. So if you want to avoid running different processes or avoid threads, the async.io is the way how to do the concurrency the right way. So we have built something which we call Pursuit, which is actually reading the data from our search API just with some Redis buffer. And it's actually duplicating the data to some three different destinations. One destination is our Skyflow ATL, which is reading the aggregated data and storing this to the analytics database. We can't store all of the data as it is into the analytics database because Postgres is not able to handle so much data, but we can aggregate them on the Redis and store just one hourly metrics to the analytics database. We can also put it into the BigQuery as we done it before, like 2 years ago, and we can send it, the same data sent to our business partner. So what Pursuit is actually doing, it's duplicating data and sending it to the three different destinations with a little of transformation. Most of it is filtering out some attributes. This is the same slide, basically the same structure. I get it back for a while. Business partner, BigQuery, and Skyflow, and this is it. In this slide, I'm just showing how the data looks like. There is not much to show about sending the request to our partner. We are just doing a reserialization from JSON to protocol buffers. Do you know what protocol buffers are? Yeah, some of you are shaking your heads. Basically, it's similar to JSON. It's a way how to serialize data, but it's in binary. So it's very much, the volume of the serialized data is much lower. Also, we are counting the searches per various dimensions. For example, for a combination of Turkish market and the Yandex flights, in this hour, we have 44 searches. It is not much data, but it's good enough for our analytics to, for example, measure the conversion rate in this market with this partner. Also, another dimension could be just route. We want to just monitor how many searches we have on different routes. So we can monitor if some route is not going up somehow or not. Also, this is data, not the raw data, but handy enough to be stored in analytics database. How we are doing that, we basically, in the Pursuit system, we basically get the data, find the right box, or the right template, and increment the number in the Redis system. And every hour, we just dump it to the analytics database. And the last destination of our data is the BigQuery. There is not much of the transformation, but in the final data, it's just a list of the search results. And at the end of it, we add one column to the search results, and it said 1 or 0. If there is 1, it means that this search result was actually bought by the customer. So the machine learning system can just focus on the attributes which could cause the conversion process, why the customer bought that. So this is the only system, the BigQuery is the only system when we are storing the data as it went through our search. Well, since I have described the system, it had definitely some issues, and this is one of them. But except this one, it's pretty flawless. We have found one issue, and it's memory leak. We are still not sure how it's memory leaking, but this is the solution. Once it reaches some life cycles, meaning iterating on some amount of incoming data, it stops, the server stops, which means that the Docker container stops. And since we are using Rancher for managing the Docker containers, it gets restarted. So it's getting restarted each day. And since we have like 54 running Docker containers with these data processing, it doesn't matter. So this is the quick deal with the memory leak. We'll definitely investigate in future, but this is just a quick solution how to delete memory leak. Restart it someday. Yeah, I guess that's all. So, question time. If you want to have a question, just raise your hands. Ah, there is. I was talking about search data, but I'm not a search developer. I am just some guy who tries to store the search results. Just, yeah. Yep, your question.
Yeah, so on one of the first slides, you were asking the question, how much does it cost? So finally, where do you store raw data? Is it Postgres?
It is BigQuery, definitely. Some of the data we are storing in the Postgres, but just the aggregated one. So it's under the 1% of the volume.
Yeah, but this is aggregated, and BigQuery is like one-to-one mapping.
Yes, it is. We may also throw away some of the data, but the most important are in BigQuery. Per each such search and also per each search result, we store it in BigQuery. Yeah.
Okay, good. And for this, how it's called, pursuit scene. So
pursuit, yeah.
Yeah, so it acts as a topic, kind of. So multiple consumers like this. So is there any like infrastructure, all is coded using Python? I mean, guys mentioned Kafka topics or something like that. So this is pure.
There is
what is the infrastructure here? Like, is it a set of Docker containers or something else?
It is just a 54 Docker containers running on I don't know how much machines, 7 probably, 7 physical machines for Pursuit. It is auto-scaled. If it's getting loaded with lots of data, it gets higher or lower automatically, so I don't really know. But last time I've checked, it was about 7 physical machines and no other system, just Pursuit with async IO. Also, we have like two just buffers, Redis buffers, incoming one and outgoing for the aggregation, but that's all. And also there is a PubSub, which is also a Google queuing system between the actually inserting into BigQuery and Pursuit. We have switched from streaming inserts to batch inserts every hour, I guess.
Okay, so a question people usually ask on interviews, like what happens if one container or multiple fails with the data it processes? So what happens to it? It will be replayed from somewhere, or it will
yeah.
Like a container is like one machine hosting many, like 10 containers. Has some hardware problem, it just stops, and we have like 10,000 records processing there just in time. And what happens?
Yeah, what happens? So if a machine fails, it gets replaced with on AVS there is auto-scaling group, so it gets replaced with a new one pretty automatically. At least I don't know about that. Maybe DevOps. If this system fails somehow, it depends what actually fails. If some of the output fails, it means we get alerted, but also it involves just one pipeline. So it means if fails, for example, sending the data to our business partner, the other buffers are not influenced by that. And if it fails that way, that the server actually stops, it gets restarted by the Docker. So it tries to boot again. And until we will solve the issue with one of the pipeline, it will not be used. Actually, there may be one thing. If the whole system is down, somehow AVS got shut down or there is a connectivity issue, the data are being stored in this Redis. It means we have like 2 hours to solve this problem, to boot up the servers again.
I see. I have the next question now. So you're probably familiar with like there is exact once delivery model, at least once delivery model, when one message can be consumed multiple times, which results in some duplicate data in the target destination. How do you solve this idempotency issue if you faced with something like data is not lost on one hand and on another hand data is not duplicated, or you have, if it's duplicated, you have a way to dedupe it?
Well,
some kind of.
Considering the code in the pursuit, I can't imagine a way how it could be duplicated, because once we read the data from the Redis, it gets immediately deleted. So it can't be read again. And we are not considering the case where the search is actually putting the duplicates data to the Redis. So that may be an issue. If we are actually getting the duplicated data, we are not doing any deduplication. That would be maybe a good case for Kafka or other advanced.
Yeah, we had this issue with Kafka. I haven't used Redis in this particular case when like Kafka is running, it's storing like in its usual way. Message is consumed by the consumer basically, and it downs like crashes for some reason, right? And Kafka has some replay model, and message is replayed, and as a result, that old message is recovered, and we have 2 messages in the destination. So we had this problem also.
Yeah, okay.
So that's why I'm asking.
Well, using Kafka, we would maybe end up with the problem also, but since there is no such a queuing system, we haven't faced it yet.
Thank you.
So, yeah.
Other questions? No? Okay.
So we'll be around till midnight and perhaps longer. Oh, there is one thing. Okay, that will be fun. I'll just give this projector screen thingy to Gabcha, and we'll do some kind of it's a quiz basically. You will just answer questions on your mobile devices. So Gabcha shows you some funny quiz, and it will be about Python and also maybe about stuff we have said in these talks. And